we're doing more AP review. This is 2006 AB-BC free response 1. This is a calculator problem. Let R be the shaded region bounded by the graph y equals the natural log of x and y equals x minus 2. So first thing I would do is put them in your calculator as y1 and y2. Find the area of R. Okay, so that's a pretty standard first question. So in order to do that, we need to find the boundaries. We need to find this, I'm going to call that A, and we need to find this B, where they intersect. So in order to do that, I'm going to graph them in my calculator. I already picked a fairly suitable window, and I'm going to do second calc intersect, right? I'm going to scroll. I always work left to right, so I'm going to scroll to the first point of intersection, the one that I called A on my visual, right? And I'm going to scroll to where the graphs intersect, and I'm going to hit enter, enter, enter. Now, when I do that, it's going to give me an x comma y. If I quit out, second quit, and I press x, it's going to give me that x coordinate. So I'm going to I'm going to hit x, and I'm going to store that as alpha a. So from now on, so I'm going to write it down just once for the AP. I'm going to say, okay, I know that a is approximately 0.15859433996. I'm going to write the whole thing, right, just once. And then I'm going to go ahead and go back to my graph, and I'm going to second calc intersect again, right? And, oh, if you want to go the shortcut, press down to get onto the line, which is slightly shorter, and it'll take you a little bit less time. You're going to scroll up to where the graphs intersect, first curve, second curve, guess, so I hit enter 3 times, and I get an x value, which is like pi-ish. It's not pi, but it's 3.14 stuff. So I'm going to quit out again, and now when I hit x, it's going to give me that nice 3.14 stuff, right? So I'm going to stow that as alpha b, right? And now I just write it down one time for the AP. So I'm going to say cool, and my b is approximately 6193221, right? I write it down one time. So when I go to do my part A is the area of this shape, so it's going to be the integral from a to b, which since I wrote them down here, I just have to have them once, right? Of my top curve, which in this case is the natural of x, minus, in parentheses, my bottom curve, which is the x minus 2 with respect to x. You have to write it out this way. The reason you have to write it out this way is they didn't call them f and g. They called them just both y equals. You can't call them both y. You can't do y minus y. You can't label them y1 and y2. So when you put this in your calculator, you're going to do it by doing function integrate, which is math 9, in parentheses, y1 minus y2, comma, with respect to x from a to b, typey, typey, type. And you're going to get that your answer is 1.949, and that's your answer, right? The AP wants to see this work. They don't want to see the calculator syntax, right? But you have to know how to do the calculator syntax, or else you have all sorts of problems. All right. Part B, find the volume of the solid generated when R is rotated about the horizontal line, y equals -3. Okay, so there are a couple ways to do this. So here's the horizontal line, y is -3. It's like somewhere down here. We're gonna call that y is -3. So if I inch over here a little bit to give me some space, right? What's happening essentially is here's my -3, right? I've got this like weird slicey shape, and I'm taking this and revolving it around that axis, so I'm getting what we call an annulus, right? This is a washer method problem, right? So what's gonna happen is as I revolve this thing, right, I'm going to take, I think we have the green marker somewhere. There it is. All right, so I'm taking some arbitrary slice in the middle. I'm revolving it around. I'm revolving this around. So what's going to happen is I have essentially a big radius, right? So what's happening is we have this big circle minus this little inside circle, right? The big circle is the top radius, right, which is top minus bottom. So the big radius is going to be top, which is natural log of x, minus bottom, which is minus a -3. Right? My little radius is going to be from this axis of rotation to the lower curve, so my little radius is going to be the lower curve, x minus 2, minus a -3, right? Now, it's not wrong to leave it looking like this, right? So the area of this circle would be pi big R squared, and the area of this circle would be pi little r squared. So the area of this whole annulus shape, one slice of this annulus, is pi big R squared, which is natural log of x minus a -3, quantity squared, minus pi little r squared, which is x minus 2, in parentheses, minus a -3, whole quantity squared, right? And so then my volume is going to be what happens if I add all of the little slices that I have, which would be the integral from what I called A to B, right? And those A's and B's were referenced in my part A, and I can keep using them as long as they're the same letters. of pi. And again, I think the AP probably chose to make this a +3 instead of a minus a -3, but you don't have to. Minus, and then a pi, and then this x minus 2 +3. And again, if you want to make x minus 2 +3 into an x +1, you can, but the AP didn't. It wasn't worth it. So that's the setup they want to see. You're getting 2 points for this complicated integrand, and you're getting 1 point for the limits, constant, and answer. So when you go to put this in your calculator, it's up to you how you would do it. Here's what I would do. I would do pi, function integrate, right? Remember that I called natural log of x my y1. I would suggest that you go ahead and note that somewhere in your paper so that later on, when you have to use them, you remember which one you called which. So I have the pi in front because I factored the pi out for both of them. And I would say that this is in parentheses y1 plus 3, quantity squared, minus y2 plus 3, quantity squared, comma, with respect to x from A to B. That's what I'm typing in my calculator. And then when I type, the answer that I get out is a 34.198 or 99, depending if you round or truncate. Again, this is what the AP wants to see. But if you can't type it in your calculator, you're kind of dead in the water, right? All right, let's talk about part C. Write but do not evaluate an integral expression that can be used to find the volume of the solid generated when R is rotated about the y-axis. So, me personally, I would do this as shells, but the AP doesn't test shells anymore. I don't know why. I'm going to do it as both options because that's just how I roll. I'm going to show you both of these options, right? So, in part, sorry, my bad. So part C asks me to take this same shape, right? So this same like shape that's right here, right? And what they want me to do is they want me to revolve it around the y-axis, right? So I'm taking this shape and going this way. Now the way I learned to do this, and I don't mean to be one of those people that's like, back in my day, we did blah, 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 but that's kind of what's happening here. So there are two ways to do this. You can either do this as shells, and the logic for doing this as shells is that your axis of rotation is parallel to your little dx slice, right? Your axis of rotation and your little slice are parallel. That means you use shells, right? That's how I learned it, and that's what I'm going to show you, but then I'm also going to show you the way the AP suggested doing it. The other reason I think you could do shells very easily here is that there is no incentive. You don't even have to integrate it. You just have to know how to set it up. So the concept behind shells is that discs and washers use the area formula for a circle, or for an annulus, which is the pi big R squared minus the pi little r squared. But either way, they both use pi r squared. But the idea behind a shell is using circumference. I'm going to show you why. If I can, I don't know if it'll work with the computer angled down the way it is, but I'm going to try it. So I got a piece of paper here, right? So pretend that you have like a Coke can, right, or like some kind of a soda can, right? It's a cylinder, right? Like you can see the cylinder. I'm not doing a great job at showing you, but you can see it's a cylinder, right? If I cut a line down the side of the cylinder and cut it open, oh look, it's a flat piece of paper, right? In fact, not just as a piece of paper, but it's the same height as the soda can, right? So like, so my soda can had this height, right? So let me try and show you here. So my soda can has this height, right? This narrow height. But the width of this piece of paper is the circumference of the circle. It's 2 pi r. So essentially the idea is that if you take one of these infinitely thin shells, right, like a piece of paper or the soda can that's cut along the side, right, and you were to lay it flat, it would essentially just be a rectangle that has the same height as the cylinder, but this measurement around the edge would be a 2 pi r, right? So shells is the idea that what you're doing is sort of doing rolls of toilet paper. There's a little shell in here, but there's a shell right outside of it, and there's a shell right outside of that, and there's another shell outside of that. And so essentially what you're getting is sort of like either a roll of toilet paper, or if you picture the like streamer paper, the crepe paper that you can get to hang out for someone's birthday, it's got expanding shells that get wider and wider until you get all the way out here, and then you'd have a really big shell, right? Like that. Okay, so if you get how shells work, then what you're basically doing is figuring out the radius, right? Which in this case, if I can steal the red marker, the radius is this measurement, and you're figuring out the height, which is just top minus bottom like it always is. So in this problem, the radius is just the distance from my arbitrary x to the axis. So that would be, I would do right, which is just some arbitrary x, minus left, which in this case is my axis of rotation, which is 0. So my radius is just x. And the height is top minus bottom, which in this case would be the top curve minus, in parentheses, the bottom curve, right? The area of one of these shells, right, is 2 pi rh, which would be 2 pi x times this whole ugly monstrosity x minus 2, right? And that's fine. Okay, so but that means the volume would be what happens if I integrate all my shells. So I'm just going to integrate from a to b, where a is the smallest of the shells, the one that's right on the inside, and b is the one all the way out here, right? And I'm going to go ahead and put a 2 pi in front, r times this h. So this is the shell method, right? So that's how I would do this problem, and it's not wrong. And I didn't have to integrate it, and that's my final answer, right? It's a minus. So that's one way to do this problem, is as shells. That's not the way the AP intended you to do it in 2006, because they like you to use disks and washers, which is fine. My personal take is that I don't usually change which variable I have solved for unless I have to. So in this case, by using shells, I didn't have to change what my equations were solved for, and it was a little bit easier in my opinion. So I'm going to write my shell answer. Well, I'm just going to erase my shell answer because it's a video, so you can pause or rewind. So now let's do the answer the way the AP wanted you to do the answer. They wouldn't mark you wrong for doing shells because they didn't specifically say, hey, you're not allowed to do shells. Just because that's not their intention doesn't mean that it's wrong, right? So if we do the other option is that instead of having my slice go this way, dx, I want my slice to go this way. I want a little, so I want a dy slice. Well, in order to use a dy slice, I must solve my equations for x. I have to solve my equations for x, right? Instead of using a dx slice, I'm going to use a dy slice. I'm going to rotate this around, and I'm going to get an annulus, and it's going to be pi big R squared minus pi little r squared. There's a couple things here. Number one, I have to solve my equation for x. And number two, my bounds are now y's, not the x's. And so that's going to provide a little bit more of a trick, but that's okay. We can totally do it. So let's start with our two equations. So this equation was y equals natural log of x. So if I solve the first equation for y, I'm going to exponentiate and get that x equals e to the y. So that's this equation. This equation is x equals e to the y. This equation was y equals x minus 2. If I solve for x, I would probably suggest just adding the 2 over. So x is going to equal y plus 2. Great. So those are my two new equations. So now, when I look at this, my big radius is going to be the farthest right curve. So my big radius is the farther right curve, which is the line minus the axis of rotation, right? So this is right minus left. So I'm just going to get that it's a y plus 2. The little radius is going to be this measurement from the axis of rotation to the smaller, or to the closer curve. So my little radius is going to be e to the y minus 0, or just e to the y. So here's where we have to pay a little bit of attention. If I want this bound, right, I know that this was the x coordinate, like this is a comma blank. Well, here's the cool thing. I know that y is just x minus 2 on both of these spots. So if this is the x coordinate b, essentially I can say, oh, if the x coordinate was a, then the y coordinate is a minus 2. And if the x coordinate was b, then the y coordinate is b minus 2. Or natural log of b, if you like it better, doesn't matter. So this is a minus 2, and this is b minus 2. Or you could find the actual values, but they didn't actually ask you to integrate. And it would be pi big R squared minus little r squared with respect to y. And that's also fine, right? That's what the AP was going for, right? Absolutely fine. I would have done it as, I would not have done it as washers. I would have done it as shells, but either of them is totally fine.